Okay, we're starting in chapter 13. We're starting at the end of the book. So this is 13.1. We're going to talk about probability theoretical, and experimental. So what I want to do first is I want to write down some of these words that we used to talk about probability, our everyday words for probability, because we came up with a nice list. We said probability had to do with likelihood, and I'm not writing these in any particular order. Likelihood, chance. We said percentage. We said ratio. We said fraction. We said possibility. And then we said it had to do with something happening. So I'm going to say percentage of something, and we said occurrence, we said events, so I'm just going to say if something happened. So all of these, we talked about all of these when we did our experiment with the standard number cubes and our little grid, that kind of thing. So this is how we were thinking about probability. What I want to do now is make a definition, how we're going to define probability. So this is what we do this a lot in math, is we take this idea and we say, okay, all these ways they're talking about it are nice. We're going to say this is the way we're going to talk about probability. There might be other ways, but this is the way that we're going to do it. We're going to say that the probability of an event and we'll talk about what event means in just a second. We're going to talk about that. Probability of an event. The way we write it is P of whatever the event is the number of favorable outcomes and I think outcome was one of our words that we talked about. Divided by the total number of outcomes. And the way I usually talk about it, rather than saying this long thing, is I just say favorable over total. There's our fraction. There's our ratio. Favorable, the number favorable over the number total. We talked about this when we rolled our dice, when we rolled our number cubes, when we made the grid on the back. We said, what was the probability of rolling a 2? We saw 1, 2 on the grid, so the favorable was 1, and there were 36 numbers on the grid. The total was 36. So we said the probability is 1 in 36. And favorable doesn't necessarily mean we want it to happen. Favorable is just the thing we're interested in. We could talk about the probability of, I don't know, failing a test. Not that we want to fail a test, but we would say favorable would be how many times we failed or something like that. So favorable just means the thing we're interested in. And this is our definition of theoretical probability. Because what we're using here is we're using what we know about something, what we know about standard number cubes, what we know about coins when we flip them. We're using what we know to calculate the favorable and the total. The experimental probability. Same thing, except we say the probability of our event is the number of favorable, or the number of times our event occurred or happened divided by the number of experiments. And is still favorable divided by the total. So on the front side of our sheet the other day, we counted up how many sixes we got. We would count up how many sixes, and we would divide by the total number of times we rolled our standard number cubes, our dice. That would be our experimental probability. And we saw when we talked about the results when we played the game that the experimental probability is not necessarily the same as the theoretical probability. It takes a lot of experiments for the two to be the same. So our theoretical probability, we use what we know about whatever it is we're working with. The experimental probability is we actually do something and we count. But we calculate it the same way. The number of ways something that we want to happen or that we're interested in comes out, and the total number of times that we do something. So we'll say it a lot this chapter. Probability favorable over total. Favorable divided by total. Are we good with our definition? Pretty easy. All right, let's define some other words that we used here. And which one do I want to do first? An outcome. Just means a possible result. So rolling a 7 on 2 die is an outcome. It's one possible result. An event is the outcome that we're interested in. An event can be more than one outcome. So we could be interested in rolling more than 7. That would be an event, rolling more than 7. Well, that event has several outcomes. 7, not 7, we said more than 7. 8, 9, 10, 11, 12 on 2 die, rolling 2 die. So that would be our event, rolling an 8, 9, 10, 11, or 12. It has all of those different outcomes. So event is just what we're interested in. You'll also, in your homework, they'll ask you about the sample space. The sample space is all possible outcomes. So on the back, when we filled out the number grid, when we did the game with the dice, when we filled in that grid was our sample space. We listed every possible way that the 2 die could come up. That when we added them together, every possible number that could come up. That was the sample space. All of those 36 numbers in the grid was our sample space. So with a coin, what's the sample space for a coin? What are the possible outcomes? Heads or tails? So heads, tails. That would be our sample space. For 2 coins, it gets more. There are more outcomes in the sample space. You got to have head, head, tail, tail, head, tail, tail, head. So all of those things would be the sample space. All the ways that that could come up. What would be the sample space for 1 standard number cube? There are 6 things in the sample space. The sample space is all the ways that it could come out. So what would be the sample space? 1. So there's, you're thinking of probability. We're just thinking what are the different ways that 1 die can come up? 1, 2, 3, 4, 5, or 6. So the numbers 1 through 6 are the sample space for 1 die. So we're listing, sample space just means list all the ways it can happen. That's what sample space means. Think about how big the sample space of 5, if you drew 5 cards from a deck of cards. Think how big that sample space is. All the different ways you could draw 5 cards. That's a big sample space. So sometimes sample spaces are really, really, really big. Are we good with these 3 words? We'll talk about outcomes, events, and sample space. Fair enough. All right. Couple of facts important to remember about probability. And I think you already know them. It's a number or fraction, and by number it could be a decimal, a number or fraction between 0 and 1. And if we write it as a percent, it would be 0 and what would be the 100%. Not $100, 100%. What does 0 mean? If we have a probability of 0, it won't happen. It's impossible. Cannot happen. What had a probability of 0 in our game? Rolling a 1 had a probability of 0. It was impossible to roll a 1 on 2 dice. What's a probability of 1 mean? 100%. So what does that mean? Guaranteed. It has to happen. So probability 1 means it has to happen. Probability greater than 1 doesn't make any sense. There's nothing that has a 105% chance of happening. That means that, I don't know what that would mean. It would happen extra or something. I don't know. And so we could say this at 0 is 100%. So if you're calculating probabilities and you come up with a probability of 10, you made a mistake. If it's 10%, that's okay. But if the number's 10, if your fraction is 10 over 0, or not 10 over 0, that wouldn't work. 10 over 1, you've made a mistake. Your probability has to be a number of fraction between 0 and 1, and then when you convert it to a decimal, it's between 0 and 100%. All right, we good here. All right, let's do a couple of examples. Calculating probability. So let's say we visit a calculator factory, and we at this factory the calculator makes, the manufacturer makes 20,000 calculators. We want to figure out how many are defective, but we don't want to look at all 20,000. So we look at we look at 350 of them, and find 3 defects. So these calculators aren't working right. First thing we want to do is find the probability of a defect. Are we talking about here, are we talking about experimental or theoretical probability? Experimental. And why is it experimental rather than theoretical? We're actually doing it. We're looking at the calculators. We're picking them up. We're looking at them. Are they defective? We're actually doing it. All right. So our probability, so we want the probability of, the way we'd write it is probability of defect. And we said it's favorable over total. Favorable is the thing that we're interested in. So how many favorable outcomes do we have? What are we interested in here? The defects. So how many favorable outcomes do we have for defects? 3. And how many total experiments did we do? 350. That's our probability of a defect. 3 out of 350. We could turn that into a decimal. If I divide this in my calculator, I get 0.00857. So that would be our probability as a decimal. Definitely between 0 and 1. How do we turn this decimal into a fraction? You remember how to turn decimals into fractions? Or not fractions, sorry, not fraction. Percentage. How do we turn decimal into a percent? Move the decimal place over. How many places? 2 to the right. Perfect. So I'm going to move the decimal over to here. 1, 2. And this equals 0.857%. So we have a 0.857% chance of a defect based on our experiment. So there's a probability of a defect based on our experiment, based on picking these up. Yes? Twice to the right. Yes. Mm-hmm. And now we'll convert a decimal to a percent. So not a big probability of a defect. Now the second thing this manufacturer wants to know is how many of the 20,000 based on our experiment will be defective. So what is this question asking us to do? So multiply the decimal by 20,000, because what it's asking us to do is find what is 0.857% of 20,000. To do that, we multiply the decimal times 20,000. So our defects equals 0.00857 times 20,000. That's how we find 0.857% of 20,000. We write the percentage as a decimal, which we already found out, multiply it by the number. And when we multiply this out, the number of defects equals, we come up with 172 calculators. And I think I rounded it. So we would expect, based on our experiment, that about 172 calculators out of 20,000 would be defective. So that would be our estimate based on our experiment of picking out 350 and looking for defects. We good there? Did I do the math right? Yeah. All right, good. All right. Let's look at another example, and then we'll use this next example when we have one last topic to talk about. Not too bad, right? Not too bad. The homework problems are very similar to this. Nothing really difficult. All right. This one says, and this one should be familiar. We roll two dice. Standard number cubes. We want the probability of a total of 9. So if we don't have our little chart to look at to figure out how we can come up with a 9 with two die, what I do is I make a little chart. So how, if we roll two numbers, what two numbers, how can we get a 9 on two die? 3 and, because we can't start with 2 because 2 doesn't add, it had to be 2 and 7, we don't have to. 3 and 6, 4 and 5. We could also roll the 5 first, 5 and 4, 4, 6 and 3. So it could be in either order. So how many favorable outcomes do we have? 4. We have 4 outcomes here, yes. We have a standard die, so it only has 6 sides. Okay. So we're just using the die like we used the other day on that game. All right, so favorable outcomes is 4, so the probability of a 9 equals a favorable over the total, 4 out of, and how many ways did we decide the other day? How many possible ways that two die could come up? 36. 4 out of 36. And we can reduce that fraction, right? How many times does 4 go into 36? 9. Very nice. So the probability is 1/9. So we reduce that to 1/9. Divide everything by 4. We could say 1/9. If we turn this into a decimal, that equals 0.11. We divide 1 by 9. That would be a correct answer also. That also equals as a percentage. How do we turn 0.11 into a percent? Move the decimal to the right so we get 11%. Perfect. So 1/9, 1 out of 9 chance, 0.11 or 11%. Is 1 out of 9, there's just not a right or wrong answer, just kind of to think about. 1 out of 9, is that a good chance of something happening? 11%? No. When? So again, no. This isn't a right or wrong answer. When do you think that we end up with probability of something being good?
But for the subject of test.
Sure. Yeah. There's not a. Well, what do you think? More than 50%. Okay, that's a good answer. 50-50 means you have the same chance of it happening as it not happening, right? I just wanted to see what you say. 50% is 50. Would 51% be a good chance? Better than not, right? If you're thinking of gambling money, I don't know if I'd want to bet on a 51% odds, but no. It depends on how much you stand to lose, though, right? You start getting up above 60%, and then you start feeling a little more confident about things happening, right? So, like I said, it's subjective. I'm just curious what we think. 40%, not a great chance. How about the lottery? You have like 1 in 100 million to win, so not a great chance to win the lottery. I had a friend when I was a professional juggler. He used to say, as
When you were a professional.
you guys didn't know I was a professional juggler?
No.
I thought I told you.
When you said it.
You weren't. Oh, you were gone when we did the 2 truths and a lie. Yeah.
Juggle.
I'll juggle it several times over the course of it, and I'll show a video of me back in the olden days when I juggled. So I was a professional juggler. A friend of mine used to say as part of his show, if you believe you're going to win the lottery, you have to believe you're going to be struck by lightning, because the probability is about the same. All right. One last thing that we need to talk about today is complement. And notice we're spelling this with E's, not with an I, so it's not saying that was a nice event. We're not saying nice things about the event. So it means something a little different. The complement of an event means kind of the opposite. We could also think of it as everything that's not the event. So the complement of flipping a heads on one coin would be what? What's the opposite of flipping heads? Tails, flipping tails. The complement of rolling a 6 on one die would be 1 through 5. Everything else. The complement of rolling a 6 is all the other things that could happen when you roll one die. The numbers 1 through 5. So the complement is the opposite of the event we're talking about. The nice thing about a complement, sometimes it's easier to find the probability of the complement than it is to find the probability of the event. So we want to find the probability of the complement. Well, let's think about how this would happen. The probability of an event plus the probability of everything else, which is the complement. What's that going to have to equal? 1. If we have an event and we have everything that's not the event, we add those two together, you get everything that's possible to happen. So that has to equal 1. So I can subtract whatever this number is from both sides, and I get the probability of the complement is 1 minus the probability of the event. So we can find the probability, sometimes it's easier to find the probability of complement, or we can use this formula to find the probability of the complement. So in our last example, the probability of a 9, we decided was 1 in 9. So let's find the probability of everything else. Probability of not rolling a 9. The probability of rolling a 9 is 1 in 9. Everything else is not rolling a 9. Every other possible number other than 9. We would say that is 1 minus 1/9. How do we subtract these two numbers? We have to turn our whole number into, what to say, a fraction? And when we turn into a fraction, what has to be the same between the fractions? Denominator. We have to find a common denominator. What's our common denominator here? 9. So I'm going to multiply to find the common denominator. I multiply this by 9 over 9. And I multiply these together so I get 9 over 9. 9 over 9 times 1 is just 9 over 9. Minus 1/9 equals 8/9. So the probability of not rolling a 9 is 8/9. That's a pretty good chance, right? 8 out of 9, that's pretty good. So that's how we find the probability of a complement. Questions on that example? All right, I want to look at one last example and then we'll be done, having to do with complements. All right, so in a lot of probability problems, they like jars full of marbles. So we have a jar with 10 red, 8 green, 5 blue, and 6 white marbles. We want to find the probability of not picking red. Probability of not red. And I want to do this two ways. I want to do it kind of one way that involves a little more counting and one way that involves using the complement. So what's one way that we could do this? Probability of not rolling or picking a red. Yes. We add up all the marbles, basically all the marbles that aren't red, right? So how many marbles are not red? 19? So 8 plus 5 plus 6. And how many total do we have? How many? 29. This is our favorable. Those are the ones that are not red. And that's the total number of marbles we could pick from. So what do we say this was, 19? So the probability of not picking a red is 19 out of 29. Let's calculate this using a complement. Let's find the probability of picking a red. What's the probability of picking a red? 10 out of 29. Our favorable is 10. We have 10 red out of 29. The complement probability is not red equals 1 minus 10 out of 29. And we do the same thing that we did before. What's our common denominator here? 29. Multiply by 29 over 29 to get a common denominator. So we get 29 29ths minus 10 29ths equals 19 29ths, just like we got doing it the other way. You can do these problems either way. Some of the problems will say use a complement to find such and such, and what they want you to do is do this process, just showing that you understand what a complement is. Sometimes on more complicated probability problems, it's easier to find the complement than it is to find the probability we're looking for, and then you can just subtract from one and you're set. Questions? All right. Homework? There's our homework. I want to talk really quick.